Okay, the last talk is by Sizhen,
Yep.
Bian, and
Hello. Okay. Hello, everyone. My name is Sizhen from ETH, and thank you for being here. I will present my work titled with Evaluating Spiky Neural Network on Neuromorphic Platform for the Human Activity Recognition. So the background of this work is that AI is emerging in every aspect, but there's a very important challenge for AI is that the training and running AI model in age of cloud consumes a lot of power. So there's a report that by the year of 2027, there will be like 0.5 global electric power will be consumed by the AI infrastructure. So is there an alternative way to run the AI at the edge or at the cloud? And now we have alternative solution, the spiky neural network, which is a neural network that mimics the processing mechanism of the array. So the motivation is that firstly, we need to pursue the computing efficiency in edge scenarios from both sensing to the computing. As you know, there's a lot of edge scenarios that has very limited hardware resources, like the memory size and also battery capacities, like those smartwatches and those nano tools and wearables, medical smart patches. Another motivation is that to supply, there's a lot of cases that we need to supply an end-to-end solution with closed-loop feedback in ultra-low latency. Like there's very special or typical application like the eye tracking application. So normally in traditional solution of eye tracking is that you put a general camera in front of the frame of glass, but this kind of cameras are very slow in speed, like every second there will be 60 frames, but that's not fast enough, like because the pupil moves super fast, like sometimes it moves over 300 degrees in 1 second. So just the sensing is not fast enough. And if you consider also the computing part, it will take a lot of time to give you every position of the pupil. And the second motivation of this work is that there's a rising trend of spiky neural network and also the neuromorphic processors for energy efficient edge or cloud computing. So this work will give an answer to this question. Is neuromorphic solution more energy and time efficient than the state-of-art traditional edge solution in edge scenarios? So spiky neural network that mimics the biological neurons in the brain. Here you can see this figure. This is a cell of the brain. Basically, the dead right will receive or perceive all the spikes, input spikes, and then the memory potential will be changed if there are more spikes coming to the cell. And if there's a fixed threshold, must the memory potential exceed this threshold, then there will be a spike being generated and being sent to the synaptic. So this is a basic model of the cell in the brain, and in current AI models, the neural model is a different, like it's a logical unit with some multiply and add logic computing. So this is totally different between spiky neural network and deep neural network. And one most important feature of spiky neural network is that the input and output, this is the map between this input and output, the function is not differentiable. So it's not possible to use back propagation for training a spiky neural network. But there's, so recent years, there's a lot of work to address this issue. And some of them will use some surrogate gradient to address the back propagation to train a spiky neural network. And there are some related works. As you can see, Sizhen, ubiquitous computing, actually this topic is very, very limited. The amount of such topics is very limited. Those are some some works that I have found from the literature, like hand gesture recognition, heartbeat classification, and they use different training mechanisms for the spiky neural network, and they deployed it on different neuromorphic platforms like Louis and Exelo, Dynap. Some of them are coming from the company, and some of them come from some research institute. And one common phenomenon of those works is that none of them report the energy and inference, energy and latency during the inference in the real in the age with a traditional solution. Okay, so this is a pipeline of the end-to-end neuromorphic solution for human activity recognition. So first you read the sensor data in analog form or digital form, and then you code those signals into spike trace, basically just 1 or 0 that represents the positive spike or negative spike, and then you train a spiky neural network, and this training need to be performed by a customized framework that can be matched into a neuromorphic processor. And in this case study, we selected this RecGym dataset, which is using the IMU's sensor and body capacitive sensor to recognize which kind of exercise a user is doing in a gym studio. And first we did the encoding, and here we use multiple threshold data modulation to encode the digital signal into the spike trace. So we move the pipeline from the traditional solution into the neuromorphic domain. And here is an example of how the spikes looks like in the 707 channels here. So this is basically input of the spiky neural network. Okay, so there are two ways to try a spiky neural network. First is you try a deep neural network, but with some variated ReLU activation functions, and then you transform this deep neural network into the spiky domain. But the feature of this solution is that you need to accumulate the events, and then you get some dense representation of the output. So basically you try a traditional deep neural network, and then this way the accuracy will be like preserved, but the temporal resolution will be sacrificed. And then another way is to make a direct event training, and this approach will keep the temporal resolution, but also at the meantime it will sacrifice the accuracy. And we used a very straightforward spiky neural network, just with 2 convolutional layers and followed by 2 dense layers. And the framework is layer, which is a customized framework for the ISO that can be trained and deployed on the neuromorphic processor of Louis from Intel. And this is the result. So you can see with multi-threshold digital-to-event encoding, we get very comparable accuracy to the traditional AI approach. And also the inference latency falls a little behind the state-of-art latency from the GAP8, which is a RISC-V-based micro processor. And it has like accelerator for the deep neural for the convolutional computing. And the limitation is mainly caused by the x86, which is the core to on the Louis platform to feed the spikes to the neuromorphic unit and then get the output from neuromorphic unit. And also the neuromorphic pipeline outperforms the dynamic energy consumption, which results in like 2 times better of the energy delay product. And the conclusion is that this work quantitatively demonstrated the efficiency of neuromorphic solution ubiquitous computing that pursues latency and energy efficiency. And this is not the end of this direction. There's a lot of following work going on. For example, we are building some analog front end that can transform directly from the analog signal to the event signal. So it's an analog front end design. And also we are doing some asynchronous event reading interface at hardware side, and also exploring some newly released neuromorphic real processors really at the edge. Okay, thank you. Any questions or comments?
Thank you, Sizhen. So during waiting for the several questions, please, speakers, please come to the front for the next panel discussion. Okay, we will take one question for him. Any question? Okay, so I have one question. So this is also better for hardware implementation, right?
Yes.
Fit to hardware implementation.
Yes.
Maybe there would be some trade-off between energy consumption and the accuracy or something like that in the future, right?
I mean, to evaluate the performance of ASIN really relies on which neuromorphic platform, the hardware side you're using. Louis is actually not for the edge, but it is a general neuromorphic platform. I think, as I said, there are some new neuromorphic edge processors coming out. For example, there's Exelo neuromorphic processor from CSS, a startup in Zurich. And we are evaluating now the performance of this tiny neuromorphic processor. And this is really hardware dependent. Yeah.
Thank you very much.
Thank you.